a pity that I could not be there in person, but yeah, this time I had to assist only virtually. So today I wanted to talk to you a little bit about applications that we are, for which we are using ptychography. And in particular, one of them, John Miao already discussed it, is the application of 3D magnetization. So I will show you some of the work that we started to do here in the SLS in this direction. And the other one is application of ptychography to do chemical characterization via XANEs, combining XANEs and ptychography, so X-ray absorption, near-edge spectroscopy. So first I will try to give a general overview of ptychography. Let me just click here and see. So in general, in a very general way, imaging can be seen as an inverse problem. And one of the most important things that we have in order to solve this inverse problem is to have a good enough physical model of the interaction between the incoming wave and the object. A second thing that is very, very important is to have diversity, enough changes between your illumination and your sample that encode the information that you want to extract. So for example, for the case of magnetization, we need to have the circularly polarized light that actually gives us the extra information on the magnetic moment. For the case of spectroscopy, we need to change the X-ray energy. But it can be as simple as scanning the sample with respect to the beam. That's one form of diversity that ptychography benefits from, but also scanning transmission X-ray microscopes. It's encoding spatial information by scanning. If you want to do 3D reconstructions, we know that the diversity that we can benefit quite a lot from is rotation of the sample. So all of that changes the data that we are measuring or the wave field that exits the sample and can give us enough information to do a multidimensional reconstruction. So here R can be the dimensionality of the sample in 2D, 3D, or in time, or in spectra. O is a function that describes the interaction of the beam and the sample. It can be a scalar, a vector, or a tensor. If it's a vector or a tensor, it also captures local anisotropy of the sample. And then finally, this signal that exits here, we still have another tool in our disposal, which is doing some modulation and then measurement. So this can mean, for example, a very useful thing for lens-based imaging is to have a modulation based on a lens that basically re-encodes the diffracted wave so that it forms a real space image on a detector here. But in other cases, you can have different types of measurements that are based on diffraction, fluorescence, photoelectrons, etc. So for the particular case of lens-based imaging, this is a very fundamental introduction for people in the audience that may not be so familiar with this. Here we have an incident illumination on the sample, then a lens is forming a magnified image of the sample on the detector over here, and the resolution is given by the wavelength and the numerical aperture of the lens. So if the wavelength is very small, as it is in the case of X-rays, one can aim even at atomic resolution, but then the numerical aperture of the lens becomes a problem. And here we can see an example why, that here we have, in order to have in this diffractive lens enough efficiency of the diffraction, we need to have zones that are high, but at the same time, the resolution is equal or proportional to the smallest feature that we can write on this zone plate. So this becomes a very challenging problem because you have very high aspect ratio structures that then become difficult to manufacture with enough precision. And so then one of the techniques that we do is we get rid of the imaging lens and we do coherent lensless imaging. Now here, the special thing is that now we have to have a coherent incident illumination. So we have to go to synchrotrons to have a coherent fraction of the illumination. We measure the intensities on the far field, and this is basically proportional to the Fourier transform, and then we use an iterative algorithm to reconstruct the wavefront here. The resolution in this case is also given by the wavelength, but now the distance is from the object to the detector divided by the diameter of the detector. So the detector is serving as an effective entrance pupil, and the algorithms are serving as the effective lens. They are serving as a computational lens. It was also mentioned. And John also showed some of this importance of the phase. There's a slightly different slide here, but it has the same idea. So here, if the original object that we wish to reconstruct or image, if we take a Fourier transform, this is the intensity that we would measure in the detector. And for each point, you have a different intensity value, but the corresponding is a complex valued function, and the corresponding phase is lost. This cannot be measured. So then if we were to take only the intensity and compute an inverse Fourier transform, then we get the object autocorrelation, or in crystallography, it's called the Patterson function. And this contains a lot of useful information about the object, but it's not an image. So we would, in order to get back to the original object, then we have to solve for this phase. And there is a variety of phase retrieval algorithms and techniques that have arisen to try to solve this problem. And back in 2011, I think we submitted a paper on using maximum likelihood algorithms for ptychography. And one of the reviewers had a bit of an inspired text over here that stuck with me for quite some time. So it reads, just as the proper grinding and coating of lenses is key in the construction of a physical microscope, the performance of the lensless microscope, specifically its resolving power, depends critically on the implementation of the basic algorithms. The basic is in the details, and this is no exception. So John was also touching slightly on this thing of getting caught in local minima, algorithms that are able to escape local minima. There are also algorithms that are statistically aware of the nature of the statistical noise, for example, like the maximum likelihood algorithms. And one thing that we hear often is, okay, you can use whatever phase retrieval algorithm, you will get an image anyway. And that is very true, especially in the case of ptychography that is very robust. It can be very true. But at the same time, we have seen that the choice of the recipe or the right algorithms to use can give a very substantial improvement on the image. So just to leave you with that there. And ptychography is one way, as I mentioned, of adding diversity to the reconstruction. The basic idea, compared to CDI, which I described earlier, is that now we have an incident wave on the sample. I hope you can see my mouse, by the way, but if not, let me know and I get, okay, I see some nodding faces. So for ptychography, we need to have a spatially bounded illumination. And in this case, I am exemplifying it with a pinhole or an aperture, but more modern ptychography uses a converging lens to have an illumination on the sample here. Then the exit wave field propagates to the detector, and we measure the intensity of the Fourier transform. And the key of ptychography is to translate or scan the sample to different positions with respect to the beam. Now, in conventional CDI, if we were using just one intensity measurement, we would have this point of the object contribute to one diffraction pattern, and that's the equations that we have in order to solve these unknowns here. In the case of ptychography, because of this overlap that you always have to have in the illumination, you have this point constrained by 5 or 10 or even 20 different diffraction patterns. So we are increasing the number of equations by which this point is constrained, and this makes the problem much more robust to stagnation and to noise and to ambiguities. And it also allows to image extended samples because you do this scanning and you can basically, as far as you can scan, you can have a reconstruction. And the resolution is finer than the illumination and than the translations. And I will come back to that with this example. So here, this is a two-dimensional ptychography measurement that we did back in published at least in 2014. And here we have what I mentioned, the condenser making the illumination here of about 10 microns after the focus, where the beam is about 10 microns, we put the sample. And this sample was an integrated circuit, part of it was a thinned Eiger detector. It was one of the first measurements we did with the Eiger. The average step size was 3.5 microns, and this is what the data on the detector actually looks like for this type of ptychography measurements. And if I run the movie, this is about twice of the real data rate that we have typically. So here you see how the different diffraction patterns look like, and then after we do the reconstruction, then you can get this is the phase of the reconstruction. You can see the integrated circuit, and the resolution that we got is 41 nanometers. So I just wanted to stress the point that the beam is 10 microns, the step size is 3.5 microns, but the resolution can be much, much lower than that, in this case down to 41 nanometers. And here you see the logical unit of the Eiger detector, the single pixel. And if you zoom in, we can see all of the different metal layers that we expected to see, since we have access to the to the design file for this detector. But of course, because it's two-dimensional imaging, then all of the features of the metal layers are on top of each other. And so in order to improve that, we have to go to 3D. Just wanted to point out all the reconstructions that I will show are done with this TychoShelves software that we published not so long ago. This is basically based on the algorithms that we have developed at the CSAX beamline. And then as the needs for more sophisticated are more modular and, to include different detectors and to include different reconstruction algorithms. As this evolved, at some point we decided we had some tools that could be useful for other people. So this is freely available. It does use MATLAB as the front user interface, and behind it we have some optimized engines with C++, GPU CUDA. It supports distributed computing, multiple GPU cards, at least with the C code, and it has different engines that are either some of them are highly optimized by scientific computing here in PSI, and the other ones are prototype code, basically MATLAB and CUDA, that is more easy to explore new algorithms there. You can concatenate different algorithms, and they have all of the different types of reconstructions for ptychography that have been out there. So anyway, moving forward, once you have a two-dimensional reconstruction, you can start to think about doing three-dimensional imaging. And for this, the basic requirement is to do a two-dimensional ptychography scan and then being able to rotate the sample at different orientations. So with the right instrumentation, you can get very high resolution two-dimensional projections, and you combine these projections from different orientations to obtain a three-dimensional model of the object. So here are these, ptychography will give you these two-dimensional complex value projections, and they are related to the integral along Z, or a projection of the complex index of refraction. So by doing the tomography reconstruction after some post-processing alignment and alignment that I will not go into detail, you can recover quantitatively the three-dimensional index of refraction. So for this type of nanoscale imaging at the CSAX beamline, we have basically two different modes of computing this 3D ptychography, of measuring these 3D ptychography datasets. One is rather conventional ptychographic tomography, where you have a sample that is basically defined as a pillar of diameter between 10 and 100 microns. And it is defined as a pillar, prepared as a pillar, so that you can access it from 0 to 180 degrees. The second one is ptychographic X-ray laminography. The difference between these two is that the axis of rotation for the laminography is not 90 degrees with respect to the X-ray beam propagation. So here we have X-ray beam propagation is 90 degrees with respect to the rotation axis. And in the case of laminography, we have a smaller angle. In the case of our end stations, is 60 degrees. So this means at this 60 degrees, instead of having to mount a sample that is microns in size, I can mount a very extended sample that, in the case of the setup that Mirko Holler built, we can mount a flat sample with an area of about 10 by 10 millimeters, and we can have any part of this sample accessible for three-dimensional imaging. So this, of course, can be very valuable for cases where, even though when you make this pillar and you measure it with ptychographic tomography, the sample itself is not destroyed during the measurements, it's a non-destructive measurement. By extracting the sample, you destroy the sample around this pillar, and so this sample extraction is by itself a destructive process. And so for some samples that are very precious, or if you want to preserve the sample in its original context, or if you want to be able to choose your field of view dynamically during the measurement, then the laminography configuration can be quite useful. And so now I will show you another example where we measured another integrated circuit. In this case, it was a 16 nanometer CMOS FinFET, and now at 20 nanometer resolution, and this was in laminography configuration. So here we have the overview of about 300 microns that we measure with low resolution, and then we can focus on some area of 40 micron in diameter to measure with high resolution ptychography. So you would see the upper layers that have the big features, the large features. And as you go down, the zero metal layer, in this case, this one. Here, the line separation of this, the line separation of these features is about 30 nanometers, and is very well resolved. And then as you go up into the different metal layers, then the features become larger and larger until you can actually connect microscopic connectors there. We also had there an inverter circuit. And since we have the design model for this inverter circuit, then we can directly compare imperfections in the manufacturing, or how well-rounded these corners are, how straight the lines are, etc. So it can be quite a useful technique in order to inspect or examine as the manufacturing of electronic circuits becomes smaller and smaller. This task becomes more and more challenging, and it complements well electron microscopy. Of course, can get very high resolution on very thin slices, and this one complements it by being able to acquire bigger volumes. So now I'm going to move into the two topics that I mentioned in the introduction, and one is magnetization vector tomography, which was a topic that John was touching upon. So to motivate this, basically, every time that you have different types of contrast, different types of interaction between the beam and the sample, this is an opportunity to extract information from the sample. So in this case, we have X-ray magnetic circular dichroism. And very briefly, the way that it works is that if you have circularly polarized light, and you have this magnetic moment, and you tune the measurement to energy of resonance, with in this case is the iron resonance. Then, if your circular polarization matches the moment of the local magnetization, then you get increased absorption. If it's perpendicular, then you get no enhancement of this absorption, and if it's antiparallel, then you get a decreased absorption. And so here, for example, here's an example of two-dimensional imaging of thin samples, where you can see the different magnetization domains. So the scattering factor, as you see, so the scattering or the absorption factor as well, depends on the Z component of the local magnetization. And for soft X-rays, you probe directly these changes in the valence band, so you get quite a strong signal. So absorption changes by a few percent or even 10%. For hard X-rays, you get this change indirectly in this valence band. So this means we have a very weak signal. So changes of contrast on the order of 0.1 or 0.01%, depending on the material. That makes it quite a challenging contrast for working with. There are different techniques that have emerged over the years to do 3D in magnetic investigation. So of course, TEM obtains the best resolution. This is already an older result. But with TEM, you can get resolution below 10 nanometers and really probe in much detail these complicated magnetization structures. In the soft X-ray regime, you can also do, for example, this is an example to do tomography, where what they did is, because the penetration of the sample is so limited in soft X-rays, they took a flat sample and they managed to roll it. And then they studied how the domains behave differently in this curved geometry compared to the flat geometry, which is very interesting, but still leaves out the ability to measure bulk samples. So samples where you have three-dimensional magnetization structures that extend for many microns. And so for this, we wanted to develop this magnetization tomography with hard X-ray tomography. So the first step is to get circularly polarized light, and this we get with a diamond faceplate near to Bragg condition. This creates a birefringence in the hard X-rays, and we can very effectively convert our linear light from our undulator to circular plus, circular right, or circular left. So here are two-dimensional ptychography scans with some magnetization stripes, and these are just some nanostructures that we deposited in order to make sure that we get the same positions. And here you see how the magnetization contrast when we switch the circular polarization. you see how the dark domain becomes a bright domain, and if you take the difference, then you have this XMCD signal. So once we managed to establish two-dimensional imaging, we move to the three-dimensional case. Sorry about that. So here we have again the diamond crystal as faceplate to convert linear light with the, in the end, the circular light that we obtain is pure up to 99.9% circular light. We have this 5-micron gadolinium cobalt pillar that we measure. First, we measure it with normal tomography, and then this is something that also John touched upon. If you notice, we are only going to sense magnetization in the direction of the beam propagation. So if we rotate perpendicular to the beam propagation, then the magnetization along the y direction, or perpendicular to, or parallel to the rotation state, that magnetization we will never be able to probe. So then we need to add a secondary measurement. So in the case of John was showing was different tomography axis. Here we remounted the sample at a different orientation with respect to the axis of rotation, and then we can get sensitivity to this missing component. And here we have an absorption image, and this is an XMCD image where you see already that the magnetization texture is more complex, more subtle than in the 2D case. And of course, we needed to develop as well a new vector tomography algorithm. Just to go, the reason why you need to develop a new tomography algorithm is that for conventional tomography, each voxel of the sample provides the same absorption independent of the direction of the X-rays, right? So here is a magnetization moment voxel, and if we do tomography, we have several of them, and we integrate along the direction of the beam. So here, if you focus on this particular vector, you see that the contribution of the magnetization is quite large, but if we go to 90 degrees, you see the contribution of the magnetization of this voxel is very small. So what we have is basically, as we rotate the magnetization of each voxel with respect to the beam, we go through different voxels, and each voxel changes its contrast. So we have to model this properly and put it into a proper reconstruction algorithm. So the way that we solved this problem was first, as I mentioned, you set up an accurate enough forward model. So this is how the scalar projections that you measure in the end depend on the non-magnetic component, and here is the magnetic component of the scattering factor. Now, we can simplify this quite a lot by doing discretization. So here we have the discrete projection in terms of the unknown magnetization and the unknown scalar contrast, normal absorption. So here you see that the only, for nth projection, we use the rotation matrix to rotate the contrast of the non-magnetic component. For the magnetization part, you see that we rotate the structure as well, and we have to add a rotation matrix outside in order to rotate the vector of magnetization. So now that we have, and then we integrate along the beam direction, which is there. So now that we have the forward model, we can establish an error metric. What we want is to find M and O such that we minimize the difference between this projection and the measured projections, or the synthetic projections. And we add over all projections and all pixels, and we want to drive this error metric as close to 0 as possible. So the first thing to compute, for example, is the gradient of the error metric with respect to the non-vectorial component, or the normal scattering, normal absorption component. And here you see already something interesting, that the update, so basically the direction by which we're going to reduce this error metric for the nth projection, or if you use all of the projections, is basically a back projection of the error. So this is very similar to what people use for iterative tomography reconstructions. They are just following the direction of the gradient descent. So we take the difference between these projections, and then we back project them to the direction where the X-rays were coming from for that particular projection, and you go downhill the error metric. For the magnetization, things are a bit more interesting, but it was surprisingly not so complicated, the difference between them. So here what we have is basically, again, the difference, so the error is going to be back projected, but we're going to multiply this by a vector sensitivity term. So basically this tells us which magnetization component was contributing, which direction of magnetization component was contributing to the projection for a given orientation. So for example, if the orientation is just 0 degrees, that means your rotation matrix is the identity matrix, and that means only the Z component, the 001, is going to be updated because only the Z component was contributing in this 0 direction. When you rotate to 90, then it's the X component, etc. So then the result is here, where we have we can reconstruct different magnetization structures. Here we have a clockwise vortex, counterclockwise vortex, anti-vortices, and we label them based on using the curl and the divergence. We could identify the ones with red are the clockwise vortex, blue counterclockwise, and anti-vortex with white. And we can, for example, this is a SUF part, 1 micron part of this 5 micron pillar. So you can follow all these complex magnetizations. And if we zoom into one part, an even smaller part of the pillar, here you see, for example, a vortex meeting an anti-vortex in height and then annihilating each other because they have the opposite topological number. This is what the magnetization structure looks like for this structure here. And if you take a look, for example, at this height, then you see the vortex, a tomography cut here. You see the vortex and the anti-vortex. And if you go higher and you go beyond this meeting point, then there's neither a vortex nor anti-vortex. It's just a domain wall that was substituted here. So, from these measurements, actually, we have, or Claire has done quite a lot of further analysis for different texture and magnetization vortices, and is quite an active part of her research now. She was in Oxford for a while, as John mentioned, but now she's a group leader in Max Planck Institute in Germany. So another thing that we did was taking this again 1 micron section of the pillar. And we found that the left part here is mostly pointing up, and the right part here is mostly pointing down. And they are separated by this 3-dimensional domain wall. And here this is a vortex domain wall. So it's basically through the domain wall, there is always a vortex going through here. And in the pillar, there was also one vortex that is the lower energy state, that the lowest energy state of this kind of magnetization structure is just a vortex through the center of the pillar. And that one we also found, and is this one here, that you see that it crosses the domain wall in a couple of places. And the interesting part is when this vortex crosses the domain wall, it's always touching the vortex of the domain wall. So they always touch here. And you can see how they switch the vorticity from one to the other, and this one also switches from right hand to left hand. And in these points where it touches, we find this Bloch point, which also John was showing some of those structures as well. So this Bloch point is a 3D magnetic singularity that basically theoretically has a 0 magnetization in the center, and they were discovered, they were predicted in 1965 by Feldkeller, but this was the first time that they were observed experimentally. And since then, of course, there are new work that has been popping out with analyzing these kind of textures. So to keep moving, then I will switch now to the second topic of the resonance theme presentation, which is basically combining 3-dimensional ptychography with spectroscopy. And in this case, just to give a very brief background, if you have here the absorption of a material versus the incident X-ray energy, you find that at low energies, X-rays are absorbed highly. Then at some point, and as you increase the energy, then material becomes more and more transparent. And at some point, you have an absorption edge. And this occurs when the incident X-ray photon matches the binding energy of the electron here, one of the inner electrons. So it is able to be kicked out. And as a result, you also have a decay of the other electrons into this orbit, and they emit fluorescent X-rays, but we are not using those fluorescent X-ray signal in this work. Then after the edge, of course, you keep increasing the energy and more X-rays are transmitted. But now this absorption edge is quite more interesting than just a boring step function. It contains quite a lot of structure, and this is the basis of this technique called XAMES, or X-ray absorption near edge spectroscopy. So, for example, in the case of these two spectra of vanadium, by analyzing the difference or the different, the height of this edge, the different height basically means different concentration of vanadium. If you change the oxidation state, then also the resonant energy shifts slightly. If you have different, this is a pre-absorption peak, and this pre-absorption peak tells you information about the local coordination geometry or local crystalline order. So it tells you something about the environment. So here the interesting thing is when we combine this with three-dimensional ptychography, we do not get atomic resolution, and we are quite far still from from atomic resolution. But you do get, even on these voxels of 20, 30 nanometers, some statistical information about the atomic environment, some statistical information of the chemical environment that is very, very valuable for these samples. And we can do that on samples that have volumes that are quite representative for the science that you want to analyze. So on the order of thousands of cubic microns. The first demonstration of this combination was by our colleagues in Japan in spring 8. And so they took, what I can imagine, this was quite a heroic experiment. It took 5 days of measurement, and they took 28 different ptychographic tomograms. So the amount of data that is needed to do that reconstruction is quite large. However, with this amount of energies, and these are the black dots here in these plots, with this number of energies, it is not possible to do a priori characterization of the chemical structure, but because they had reference spectra from the components, they could do a fitting and then determine the balance of the cerium. They would have the cerium edge in this case. So they measured 28 tomograms in this energy range, and they were able to recover the oxidation state, the chemical information of the component. And so what we wanted to do is to take this approach and being able and figure out a way to scale it to larger samples with higher resolution, with more energies, in order to avoid the need of having this reference spectra, because it's not always feasible to have this spectra for all materials. So the sample that we analyzed in this case, we wanted, basically the sample in this case is a few microns, and we wanted to scale it maybe 2 microns, something like that. And we wanted to scale it up to measure on the order of dimensions of 10 microns. So here, the sample that we were studying is this VPO catalysts. We had a sample that was pristine and a sample that was used in an industrial reactor for 4 years. These are the sample, what they look like, there's 10 micron pillars, and this was the work of a PhD in the group Sirui Gao that graduated this year. So we wanted to get these 3D nanoscale maps of chemical composition to understand how this catalyst, for our collaborators that are the energy experts, which I am not, to understand how these materials are changing chemically. And the way that we approached this was using sparsity. So we knew that we cannot, these are the X-ray energies that we measure in this case. These are 60 X-ray energies. And we knew that we cannot measure with full Crowther criterion each energy and have a reasonable measurement time. So we just measure, as indicated here, basically measure less projections for each tomogram. The Crowther criterion is basically gives you the number of projections you have to measure is proportional to the diameter of the sample divided by the, well, with some factors, by the resolution that you want to obtain. However, if you think about it, the changes of the tomogram, I mean, if you measure a Crowther criterion for each energy, this means you could reconstruct a completely randomly arbitrary sample that is completely different from each energy. And this is not the case. There is a huge amount of correlation and a huge amount of shared information. You just need to measure enough projections to capture the changes. And so overall, you can measure quite less, at least in the spectral tomography. So what we did is measure these 60 energies with 0.5 eV energy step right at the edge. And bigger step on the periphery of the edge, with only 11% of the projections of the angles that we would need for the Crowther criterion. The whole measurement of each sample took about 1 day of beam time. This is the measurement scheme, very schematized. So the angles of measurement are 0 to 180. Instead of measuring all the projections that are given here by the small dots, we only measure the large dots. But when we go to the next energy, we make sure to measure an angle that we did not measure before using a golden ratio rule. So every time the starting angle is a different starting angle, it just goes with golden ratio. So you know that you get all the angular diversity as well, because you need these different angles to be able to provide the three-dimensional information. And we used physically motivated constraints. So basically, we combined principal component analysis and iterative reconstruction based on the idea that there are only a few different chemical species that can exist for vanadium. There are only a few different oxidation states that can exist. So physically, there are only a few spectral modes that are allowed. So by using PCA, we use this modal constraint ab initio without knowing these modes at the beginning. And what I would like to emphasize is also that for the reconstruction, it would be completely inappropriate. It would not work to reconstruct each energy and then try to do this PCA or so. You have to do a full four-dimensional reconstruction of the hyperspectral data set. So very briefly, the way that it works is you have some, I will not describe it into detail, but I want to give you some flavor. So you have some projections. From these projections, you can already estimate the principal component spectral decomposition using very low resolution, 3D reconstructions that are unaffected by the undersampling, let's say. And then you use the high resolution projections and an iterative algorithm to refine. First, you refine the first coefficient. So basically, it's a three-dimensional array that looks like the sample that basically where each voxel corresponds to the coefficient of the first component. Once you are done, we remove, once it converges, we remove this component from the data and we apply the second component or refine the second component. And then we refine the third one. Here you can see actually some differences in the sample there. The fourth one, and then after the fourth one, we found that basically the fifth one was basically noise. So this is what the tomograms look like with electron density contrast. And you can see, I mean, morphologically, the sample in the reactor changed quite a lot. You can see a bit more, much better the crystals. Here you have a lot of extra matter. But if you add the chemical information, then it becomes even more striking, the difference. And here I am showing a three-dimensional encoded chemical information where from dark to bright, it is increased electron density. From grayscale to very colorful, it increases the vanadium concentration, and the oxidation state is encoded by the color. So 3.5 plus is blue, and 5 plus is red. So you can see the chemical composition of the two samples is quite different. The resolution that we obtained was about 26 nanometers. And so far, well, here is just to, oops, too far. Here is just to show you the quality of the spectra. So we operate, because it's hard X-ray, so we reconstruct the phase spectrogram here. And this is just these 2 points represent these 2 points of the sample, is the single voxel spectrum. You can do Kramer-Kronig's transformation on the phase to get the real part, to get the absorption part of the refractive index. And here you see these features that I was mentioning. Now, so far I have not talked about this fourth, the pre-peak intensity. So if we take this pre-peak intensity and we plot it in 3D, we also see very different behavior from the pristine and the used. And of course, we can extract this crystal that is extract virtually this crystal that is a couple of microns. And for the different crystals, we did computations of these quantities, these chemical quantities, for different distances from the surface. So this is here very close to the surface and as it goes into the catalyst. And our collaborators did some fitting of the spectrum from these different distances from the surface. And they found that in the surface, we had an abundance of this vanadil deficient catalytic active site, which had been theorized, but this is the first time that we actually observed it in a sense that we could also correlate it to the reduced performance of the, to the boosted performance of the catalyst. So in short, the used catalyst, even though it reduces the surface area quite a lot, it was still performing much better than it should. And these structures that we found, these crystalline defects near the edge, were the reason why it was performing better than expected. So I just wanted to touch very quickly, if I have 2 more minutes, on this electron microscopy, because John was also showing very, very impressive results. And for ptychography, there has also been some progress. So in 1969, ptychography was proposed by Walter Hoppe to basically do electron microscopy. But by then, holography was quite well established, and even lasers were invented. And so that was taking prevalence. Also, the instrumentation, detectors, the coherence of electron microscopes was not quite good enough to do good ptychography, but now we're starting to see a boom of more and more ptychography happening in electrons. So this is the collaborative work with David Mueller, where we actually use TychoShell for the reconstructions. The resolution is the highest resolution reported, at least to my knowledge now, with a thickness of 21 nanometers, which is more than 10 times the depth of field of what we should get with this resolution. Here you see even the electron beam propagating through the 20 nanometer changes quite significantly, and never mind the actual resolution of 15 picometers. And ptychography is useful because it overcomes lens aberrations and multiple scattering. We use this multi-slice technique so that we basically take into account multiple scattering and reconstruct the multiple layers within the sample. And we overcome the numerical aperture of the lens. And the reason why they say it is the title of the resolution limit set by lattice vibrations, if you take a look at a simulation of the electrostatic potential of this material at 0 Kelvin, it looks like this. At room temperature, you have thermal broadening of the electronic cloud. And when you look at the experimental reconstruction of ptychography, you can actually determine that now the resolution is really limited by this electronic broadening in this case. And so for more information, you can also, more information or different discussions of connections of ptychography to different techniques in the optical and the electron regime. I refer you to this paper that we published in last year. And first, and I would like to finally thank, it would be just too many people to show in one slide. I have so many people to be thankful for, so I show at least how the current coherent scattering group looks like. I want to acknowledge funding, and of course, just to emphasize that all that I show here is just a collaboration of many, many people. And also to advertise soon, there will be postdoc and PhD positions that I will have available. And so if you are interested in doing some of this work, please contact me. And this is just my contact website there. And so with that, I would like to end and welcome any questions you may have.
Thank you very much, Manuel, for that beautiful talk.